Well, I wanted to stop and make sure my computer was still working right and everything was recording. So let's take a look at these different types of symmetry. So we're talking about symmetry with the y-axis, with the origin, and with the x-axis. So these three types of symmetry can be a little bit helpful. Let's take a look at the first one. Symmetry with the y-axis means the graph looks the same when it's reflected across the line y equals x. So the left side looks exactly the same as the right side. And a great example of this is the standard old parabola, y equals x squared. So it goes through 0, 0, and then 1, 1, and then negative 1, 1, and then 2, 4, and then negative 2, 4. So it looks something like this. And that you can see that it's symmetric. If we were to fold this along the y-axis, with this point right here is, 2, 4, and this point right on the other side is negative 2, positive 4 also. So if we take a look at that, it doesn't matter whether we go to positive 2, we get a function value of 4, or to negative 2, we get a function value of 4. So we can generalize this idea on a function that's symmetric with the y-axis, because if xy is on the graph, so is negative x, y. So again, it doesn't matter whether we go to the right or the left, we get exactly the same function value. So this type of function is called an even function. So functions that are symmetric with the y-axis are called even functions. Let's take a look at symmetry with the origin. This isn't a fold or reflective symmetry like we had up in example 1, but we're talking about symmetry with the origin. So this is a rotational symmetry or point symmetry. And a good example of that is y equals x cubed. So it goes through 0, 0, then 1, 1. It goes through 2, 8, so 1, 2, 3, 4, 5, 6, 7, 8, so we're good there. So this point right here is 2, 8. If we go plug in a negative 1, we get out a negative 1. If we plug in a negative 2, we get out a negative 2. So I'm just going to label those points right there. And this is what the cube root function looks like. So again, you'll notice that if I were to put my pencil at the origin, I could turn this 180 degrees and it would look exactly the same. And that's the idea of this point symmetry or this rotational symmetry. That's symmetry with the origin. So again, you'll notice, let's take these points 2 and negative 2. If I plug in a 2, I get out a positive 8 because 2 cubed is 8. If I plug in a negative 2, I get out a negative 8. So again, we can generalize this idea. If xy is on the graph, like if 2, 8 is on the graph, negative 2, negative 8 is on the graph. So if you go to the left, so if I go to negative x, I get the opposite function value, so I get negative y. So this just means we're going in the opposite direction and we get the opposite function value. And again, we call this type of function an odd function. That's the name we give to that. And those come in handy quite often. And I'll let you think for just a second about this one. We don't use symmetry with the x-axis very often, and I'd like you to think about why. We've actually shown an example of why we don't like this one, or why we don't use it very often. Because if something is symmetric with the x-axis, that means the top would look the same as the bottom. So think about that sideways opening parabola that we talked about a few minutes ago. This doesn't pass the vertical line test, so anything that's symmetric with the x-axis is not a function. And we like functions. It's not that things that don't pass the vertical line test aren't useful. It's just that we like things that are functions for the most part. We use those a lot. So looking at a graph and telling whether or not it's an odd or even function, whether it has any type of symmetry, is pretty easy. But looking at a weird function, or even one that you're pretty familiar with, without a graph is kind of difficult. So let me remind you of what the test is for odd and even functions. So the test starts out the same. Replace every x with a negative x and then simplify. If you get the exact same as the original equation, then it's going to be an even function. If you get the exact opposite, then it's going to be an odd function. And if you don't get something that's exactly the same or something that's the exact opposite, then we say it's neither. It doesn't display either of those types of symmetry. Okay, so you do have to be very careful with odd functions, especially if they're rational, especially if they involve fractions, which this one right here does. So for example, if I said, what's the opposite of 3/4, most people would say, well, it's negative 3/4. Well, you've got to be careful with this because remember, there are 3 ways to write a negative fraction. You can write the negative on the top, you can write the negative on the bottom, but can you do this? Okay. Occasionally, some people will say, gosh, for some reason, when it gets more complicated like this, they'll think they both need to be the opposite. Well, that would be just the same as the original fraction 3/4. So make sure you keep track of that. Negative on the top, negative out front, negative on the top, or negative on the bottom. That means it would be the opposite. A lot of times it's helpful to pull that at negative out front, regardless of where it appears. But let's take a look at the two of these and let's run through the test. So the test is figure out what happens when we plug in a negative x. So what is f of negative x? What if we go the opposite direction from x, basically? Well, again, you'd want to plug in parentheses. If I square a negative x squared, I'm going to get an x squared plus a 9. Whoops, I should have made that a negative x. Okay, and then if I multiply here, I get a negative 3x. Well, if we look at this, is there any way this is exactly the same? It's not exactly the same as the original one, so that means it's not even. But is this the exact opposite? And then again, this is where people get into trouble. They think, well, gosh, this is the opposite, but the top's not opposite. Okay. But all we need is either the top to be negative or the bottom to be negative to be the opposite of what it used to be, and then we're in good shape. So what I'm going to do is I'm going to pull that negative out front. I'm going to rewrite this, and I'm going to put it in parentheses. Notice this is the original one with a negative in front, so that's definitely the opposite. So that means this one is odd, and there's our work to show that. Let's take a look at this one right here. Again, we're going to plug in a negative x, so I'm going to just draw an arrow, and I'm going to write 25 minus, and again, plug in parentheses. I'm going to simplify that. That's 25 minus, this would be x squared. So then I compare that to the original one. It's exactly the same, so that means this one is even. So that means this particular graph, if we were to graph this, would show symmetry with the y-axis. So let's think about what this looks like. I'm hoping you know what this looks like. This is brought up in 1050 and in 1060. This is actually a circle centered at the origin whose radius is 5. So if it's centered at the origin with a radius of 5, this point would be 5, 0, this point would be 0, 5, and this point would be negative 5, 0. So you can see that that is symmetric with the y-axis, so it's definitely an even function. Okay, now I'd like to mention a few more things and then we'll be done with this first part of the video. So there are a bunch of different ways that we can represent a function, and it's important that we know each one of them. So we can represent things graphically, which we're usually pretty good at, numerically, I mean with numbers or number sets, algebraically, which is what we've got right here. Those are algebraic representations, clearly a graphical representation here. And then we can also describe functions in words. So we've got some very common functions like this, and we understand what the graph looks like, an upward opening parabola. And again, all of these functions are useful in different situations, so it's important to be familiar with all of them. So it's important that you know what the basic parent functions are. So these are the basic graphs that everybody needs to know the shape of. So every function makes a shape when you graph it, and some of the ones that you ought to be familiar with are linear functions, polynomial functions, root functions, rational functions, exponential functions, and logarithmic functions. And if there are some of those that you're not familiar with, like say you're not very good at polynomials, or logarithmic functions tend to be a struggle for a lot of people, those might be things that you want to take a look at. In the back of the book, there are a bunch of commonly used functions that are in the back there, and they kind of go through and explain those. And you also need to be familiar with some other basic concepts from pre-calculus and some formulas from pre-calculus. So things like point-slope form of a linear equation. You're going to want to know that. You're going to definitely want to know how to find the slope between 2 points, or the distance between 2 points, or midpoints, or different things like that. And also to some extent be familiar with volume and area and different things like that for some typical geometric shapes. And again, there's some things in the front of the book and in the back of the book that can be helpful there. So let's go through and do a couple of examples that will demonstrate these basic ideas that you ought to be familiar with. So this one says, find an equation of the line that's perpendicular to this line that goes through this point right here, and write your answer in point-slope form. Well, the first thing we ought to know is, what is point-slope form? Well, that's this form right here, y minus y1 equals mx minus x1. That's point-slope form, and it's very useful, and we'll use it all the time in calculus, so make sure you know that one. In order to find a line that's perpendicular, we've got to remember a couple of facts. Well, the first thing we'd want to do is we're going to want to find the slope of that line. Well, in order to find the slope of this line, I'm going to start moving this around so I can put this in slope-intercept form. So if I move that over to the other side, that's going to be a minus 3x plus 7. And then I'm going to divide by the negative 4. That's going to be negative 3 divided by negative 4. That's going to be 3/4 x. And really at this point I could stop. This does turn out to be negative 7/4, but this is what I'm after right there, okay? So the slope of their line is positive 3/4. Well, if I want one that's perpendicular to that, I want a slope of, remember, it's the opposite reciprocal, so negative 4/3. So this is the slope that I want, and this is the point that I need to use. And I'll mention this several times in the class, and I'll ask a question this way. I'll say, what do you need to write the equation of a line? Well, you've got to have a point, which they gave us right here, and you've got to have a slope. And the nice thing about point-slope form is all we have to do is just plug that in. So we write y minus, this is x1 and this is y1. So this is minus minus 5. The slope is negative 4/3, and then x minus whatever x1 is, that's going to be a 6. So there's what we've got. I do want to clean this up just a little bit. I'll write y plus 5, then I'll write negative 4/3, and then x minus 6, and that right there would be the answer to this particular problem. Okay? All right, let's do a couple more here. So this is a piecewise function, and we'll see quite a few piecewise functions in this class. So here's how I like to describe piecewise functions. Hopefully, if I were to say, can you graph this line? Hopefully everybody would be okay with that. If I said, can you graph the line y equals 5? Hopefully everybody would be okay with that. And if I said graph the parabola negative x squared plus 1, everybody would be okay with that. Well, if we know these shapes, all we need to know is what this means right here. Well, this is the domain, or this is where it looks like that shape. So I'm going to do this in dotted fashion here. X plus 3. This would cross at 3, and it would have a slope of 1. So it's going to look something like this. Okay? But it only looks like this when x is less than negative 3. So if I kind of draw a wall right here at negative 3, it only looks like that over here, okay? So it's going to look like this piece right here. I'll put an arrow on that, and then I'll erase all this other stuff, okay, because it doesn't look like that line there, okay? And then I just need to decide, do I put an open circle or a closed circle here? Well, I put an open circle on this one because it doesn't actually equal, it can't actually equal that point. I can't actually plug in a negative 3. Okay, let's think about what this looks like. This is y equals 5, so that's a horizontal line at 5. Now, it only looks like this line between negative 3 and 0, so from here to here. So I'll erase the rest of this, okay? And it only looks like that line right here. And again, I need to figure out what the endpoints look like. Well, notice that these are both included, so I'm going to have a closed endpoint here, and I'm going to have a closed endpoint here. And then this last one, this is a parabola that opens down that's been moved up 1 unit. So it would look something like this. There would be the vertex. It would go through here and here. And it's going to look something like that. Okay? But again, it certainly can't look like that over here because then it wouldn't pass the vertical line test on this left side of the graph. So the only part of this that we're going to keep is the positive part, the side where x is greater than or equal to 0. Or sorry, just greater than 0. So I need to put, that's going to erase everything there. I need to put an open circle right here, and then that's the graph, okay? So the last thing I want to do before we finish here, and I let you work on this on your own a little bit, or go on to the next couple videos, is we want to think about how to graph a rational function. These tend to be fairly difficult for most people. So the first thing we want to do is we want to figure out what the domain is. And it says, analyze the following rational function. That means figure out everything important about it using analytic methods or technology. And we'll use a calculator just to double check our answer. So let's take a look at this right here. The first thing we're going to want to do is we're going to want to factor this. So this does factor. I can take an x out in the numerator. I'm left with an x minus 3. And then I can factor the denominator. I'm looking for two numbers that multiply to be negative 12 that combine to be positive 1. So that's going to be x plus 4 and x minus 3. Well, the domain, you can plug in anything you want into polynomials, but because this is division, we can't let the denominator equal 0. So I can't let it equal negative 4, and I can't let it equal positive 3. Okay? So everything except for negative 4 and positive 3, okay? Then it says find the roots. In other words, the zeros or the solutions or the x-intercepts. So the cool part about this is If we're going to find the roots, the x-intercepts, we set the whole thing equal to 0. Remember, to find y-intercepts, you plug in a 0 for x, that'll find the y-intercept. And if you plug in a 0 for y, that'll find the x-intercept. Well, we want to find the roots or the zeros or the x-intercepts, so we set this whole thing equal to 0. Well, the awesome part is the only thing that can make this equal to 0 is the numerator. But we want to be a little bit careful here. Remember, when we're graphing a rational function, remember this, any place but 3, this acts like a 1. So we can cross this off, and we can, instead of solving something that's a little bit more complicated, we can now start working with this right here. We've taken care of the domain issue. So what we're really after is, when does this equal 0? Well, the only time this equals 0 is when x is equal to 0. So that means the x-intercept is going to be 0, which means that's also a y-intercept, okay? By the way, can we plug in a 0? What do we get if we plug in a 0? If we plug in a 0, this is the simplified version. If you plug in a 0, you get out a 0. So there's only one x or y intercept, and it happens to be right at the origin. Okay. Then it says, how does x behave as x goes to plus or minus infinity? Well, that's asking a question about asymptotes, specifically horizontal asymptotes. Okay. So if we plug in numbers that are really big, this would be a huge positive number divided by that same huge positive number, and we'd add 4 to it. Okay, so these are roughly the same numbers. So when we're plugging in numbers way out on this end, we get something that's really close to 1. Or you may remember from pre-calculus, the way we find the horizontal asymptotes is if these are both the same degree, that's degree 2 and that's degree 2, you can take the leading coefficient and put it over the leading coefficient. So the horizontal asymptote is y equals 1. Okay. Now, that's not the only asymptote on here. You'll remember that vertical asymptotes occur when the denominator is equal to 0 and that factor hasn't canceled. So x equals -4 is a vertical asymptote. Okay, what happens at x equals -3, or excuse me, at +3, this domain issue that canceled off? Well, that turns into a hole at x equals 3. So I'm going to draw our horizontal asymptote right here. Horizontal asymptote of y equals 1. There's our horizontal asymptote. We've got a vertical asymptote at x equals -4, so I'm going to draw a vertical line. X equals -4. There's our vertical asymptote right there. And then we've got a hole at x equals 3, and this is how I like to deal with those. I like to draw a little shorter dotted line and just write the word hole next to it. Okay? So what I'd like you to do is I'd like you to stop here, see if you can finish this on your own, and then we'll pick up right there on the next video and we'll complete the rest of this. So hopefully this has been helpful. I'm hoping all of these this stuff that we do to reviews, chapter 1, pre-calculus, is helpful. Come and see me if you've got any questions. Thank you very much.